Okay, so binary search, how are we going to program it? We've been through the theory. We looked at how it works. You played around with it with the numbers, hopefully, in the list, and you've written down the lower bound and the upper bound, the midpoint, and the search item, so you can understand whether or not all these variables that we're going to have in this program. And maybe some of you have then been able to write the pseudocode, which will allow you to then write the actual program. I'm going to show you how to program it in the way they're asking this past paper question. So one thing you could do is you could copy out this past paper question in the way that they're programming it, and then you'll be able to fill in the gaps and you'll be able to understand it. So do it this way. We're going to need to create a function. So it's going to be called binary search. It's going to return an integer. It's going to be -1 if they don't find it, and the index if they do. So binary search, and we're going to pass in firstly an array of integers. Let's call that array. Then we're going to pass in a lower bound, which is also an integer. And then we're going to pass in an upper bound, and then we're going to pass in the search value. In the exam question, the first thing they do, they have a while loop, and they just say while true. Well, I'm not sure how that would work in real code. So we're going to have a different condition here. We're going to keep looping while the lower bound is less than or equal to the upper bound. So if you think about this, if every time we're adjusting the upper bound or the lower bound to be closer and closer together, if there's a point where this lower bound becomes greater than the upper bound, then we know that we've searched all the available space. So there's no point carrying on searching. So we're going to keep looping until that condition becomes true. And then what they do is they calculate the midpoint. So we're going to do that. The way they calculate the midpoint in this question is they take the lower bound. So imagine that was lower bound. Imagine that was like 5. And then they add that onto the difference between the upper bound and the lower bound divided by 2. So the average of that. So what's the difference between like 8, say, and 5? It's 3. Divide that by 2. You get 1. Add that to the lower bound. If the lower bound was 5, the new midpoint would be 5 plus 1, which should be 6. So that's one way you can calculate the midpoint. Now, in this, in the example before, I was saying you could also calculate the midpoint as the average, just the upper bound plus the lower bound plus the upper bound divided by 2, and then you get the midpoint. That would also work, but this is the way they do it in this question. And I believe, looking this up, the reason they do it in this question is because imagine you had a very, very, very big list. There are only so many numbers you can actually have in an integer, and if you're adding 2 big numbers together, like a lower bound, which could be, say it was 5 million plus the upper bound of 20 million, you could get too big a number that may make the computer crash. Go and do some research on that. Like, what's the difference between doing it this way or just doing it like midpoint equals upper bound plus lower bound? But the idea is overall it's the same. You're going to get the midpoint, which is what we need. Then they do a little test here. Now, what they're testing here is if the upper bound is less than lower bound, then they're going to return -1. Well, we've already done that in here. So we don't need to do that if statement there. But what we do need to do is we need to test what the value is at that midpoint index. So if the array at the midpoint, if that is less than the search value, right? So if the thing at that midpoint is less than the search value, then we know that we're not going to need the bottom bit of the array. We can throw that away. So which one are we going to need to update? the upper bound and the lower bound, we're going to need to update the lower bound, which is what they are, what they're doing here. So we're going to need to update this lower bound, and it's going to be whatever the midpoint was plus 1. So we're updating that lower bound. So the thing at the middle, right, is less than the search value. So our search value is somewhere here. Or looking at this example, like here, the midpoint, thing we're looking for 75, it's greater than that. So this is less than that. Therefore, we can chuck that away. So the midpoint becomes the midpoint plus 1. So the lower bound becomes the midpoint plus 1. Else, what else? Let's just see how they've done that. Else, if it's greater than, so else if the thing, the item at midpoint, if that is greater than the search value, then we're going to need to, so the thing at the middle is actually greater than the search value, so it's going to be in this bit. We're going to need to change that upper bound to be the midpoint minus 1. So looking at this example, if the thing we're looking for, like say 15, that's going to be less than the midpoint. So if that's the case, we get rid of that whole chunk, the midpoint minus 1. So our upper bound becomes the index there. So upper bound equals midpoints minus 1. Else, well, if it's not less than and it's not greater than, then it must be the item at the midpoint. And if that is the case, we need to return that midpoint index value, because we found the item. However, if this ever becomes true, right, well, if the lower bound suddenly is not less than the upper bound, the while loop will quit and we need to return minus 1. So this is slightly different to what they're saying here, just because here they're saying they have an if statement and they're saying if the upper bound is less than the lower bound, but you return minus 1 here. So that's the exit condition. But and these are the other cases which we've just written out. But we're returning minus 1 after the while loop was quit. So that's how you do binary search. How am I going to call this function? You just write binary search. I need an array to pass in. What do I need to pass into this? I need to pass in the numbers array. Then I need to pass in the lower bound, which is going to be 0, and then I need to pass in the upper bound, which is numbers dot length minus 1. And then we need to pass in the value that we're looking for. Let's say we're going to look for 34. So this is going to return an integer result. It's going to be either the index or it's going to be minus 1. So we need to check that. If the result equals minus 1, then console dot right line, we've not found the item. The number is not in the list, the array. Else, number is in the array. Have found it. The number is in the list. So we found it. Exclamation mark. The number is in the list. So that's how you do binary search. In almost the same way that they've done it in this exam question, so you can see how that code would work. Why don't you, just as a little test for practicing writing functions out, why don't you create the function for linear search? So you will need a function that is going to return an index, integer, index. It's going to be called linear search. We'll pass in an array to the array, and we're also going to need to pass in a search value. This is much easier because literally you're just looping through the array until you find the item you're looking for. How would you like that? So I'm just going to make it return -1. And let's just run this code just to make sure it works. It might take a while to do that right bit, that can be a bit slow. But yeah, as a little test, a bit of programming practice, make this linear search function much, much simpler. But this is how you do binary search. So again, to recap that, we call binary search with our numbers array for our lower bound and our upper bound, which is the length of the array -1, and then the search value. And then we're going to keep doing this, iterating over this until the lower bound is greater than the upper bound. And in that case, we've searched everything to find it. So that's our exit condition. Then we need to calculate there we go, it worked. We found it. The number is in the list, so we found that it works. What would be interesting is maybe you could find a way to build to measure how many steps binary search takes, especially with very, very big arrays. So yeah, and then compare that to linear search. So how many steps does linear search take compared to binary search? And then maybe you could generate a very big array. That would be an interesting test.